Hello, my name is Ramgopal, and I'm going to present some work on quantum approximate counting with non-adaptive Grover iterations. This work was done with Professor Ryan O'Donnell at Carnegie Mellon University. First, let's talk about the problem setup. So we are given a function f. This function maps the integers from 1 to n to either 0 or 1. And the way we are given this function is we're given access to it through a quantum oracle that we can query with inputs or some superpositions of inputs to learn about the outputs. Now, we define a quantity k to be the number of inputs to the function f, such that those inputs map to the value 1. And we can ask some questions based on this setup. So the first one would be the search problem, which is we might want to find some x such that f of x is equal to 1. We might also ask the question of, well, what is k? So how many such x's are there? So that's the exact counting problem. Or we might just want to estimate k, say to a multiplicative factor. And that is the approximate counting problem. In all of these cases, our goal is to minimize the number of queries that we make to the oracle. That is the query complexity. This talk will focus on the approximate counting problem. But first, for some background, let's talk about the search problem. So the search problem was famously solved by Grover's algorithm. How Grover's algorithm works is first you initialize your state to be the uniform superposition of inputs. Now for convenience, let's define two states G and B, which we think of as the good state and the bad state respectively. So G will be the uniform superposition, but restricted to those inputs for which the function gives 1 and renormalized accordingly. And B, the bad state, will be the corresponding thing, but for those inputs where the function gives 0. So notice that the uniform superposition is in the plane spanned by the G and B vectors originally, and these vectors are originally orthonormal. The uniform superposition is at angle theta star away from B, where theta star is arcsine of square root k over n. Now what Grover's algorithm does is it rotates our current state, which starts at the uniform superposition, further and further away from the bad state and towards the good state. And each Grover iteration rotates the current state towards the good state by 2 theta star. And so after q rotations, the angle is 2q plus 1 theta star. And when the angle is close to pi over 2, that's when we want to measure, because then we'll have a high likelihood of our measurement outcome being a state such that an input such that f of that input maps to 1. So for this, we want to choose q roughly pi over 4 times square root n over k. Note that the success probability is sine squared of 2q plus 1 theta star. And that's where we get this value of q from. And yeah, so this solves the search problem with complexity of square root n over k. Now let's head to the approximate counting problem, where we want to estimate k to some factor of 1 plus epsilon, to some multiplicative factor. Brassard, Heuer, Mosca, and Tapp in 2002 gave an algorithm for this, and this algorithm uses ideas from the quantum Fourier transform. A lower bound for this was shown by Naik and Wu in 1999. The query complexity of this algorithm is the minimum of 2 quantities. The first one is square root nk, and the second one is 1 over epsilon square root n over k. So briefly, let's talk about where these two terms come from. The main term, in some sense, is the second term, the square root 1 over epsilon square root n over k. The 1 over epsilon square root n over k term. The first term actually comes as a consequence of the fact that we cannot approximate k to a factor better than 1 plus 1 over k. So if we have a very small, if our k is very small, then we'd be better off asking our algorithm to approximate it to 1 over k, to a factor of 1 plus 1 over k, rather than to a factor of 1 plus epsilon. The reason is that because k is an integer, approximating it to 1 plus 1 over k already gives us the exact integer. So we don't need to get an even finer approximation than that. So how the algorithm works is that first we get an initial constant factor estimate, and we can do this cheaply. So we have an idea of k, let's say up to 1.1. And then we run the main part of the algorithm, which has query complexity 1 over epsilon square root n over k, but we don't necessarily pass in the original value of epsilon that we got, if we are at a k that is very small, we might want to pass in 1 over k as our effective epsilon instead to this main part of the algorithm. And so this is why, this is how we can get the square root nk term and save on the query complexity. So now we have some understanding that the main algorithm takes 1 over epsilon squared n over k time, but using this method of getting an initial constant factor estimate, we can improve it for some inputs to square root nk, which for some inputs it's better. And so the query complexity is the min of these two quantities. So coming back to the approximate counting algorithms themselves, like I mentioned, the Brassard-Hoyer-Mosca and Tapp algorithm used the quantum Fourier transform, but it seems possible that it could be done with just Grover iterations, since the speed up is very similar to Grover search, and the structure of the problem is also very similar. And so this was shown to be possible by Aronson and Rall in 2020. So they used an algorithm that their algorithm only uses a sequence of Grover iterations in order to produce a 1 plus epsilon estimate of k with optimal query complexity. And they left an open problem of whether this can be done with non-adaptive Grover iterations. So their algorithm has a feature that the Grover iterations they use are adaptive. So first of all, what do adaptive Grover iterations and non-adaptive Grover iterations mean in this context? Recall that when we talked about Grover's algorithm, we talked about how we have an initial state theta prime and we can rotate it up to some r theta prime, where r is an odd integer, and then we measure it. And with probability sine squared r theta prime, we get a good outcome, a successful outcome, which is one where our measurement outcome is an input that maps to 1 under f. So using this as abstraction, we can characterize non-adaptive Grover iterations as follows. So we first, at the beginning of the algorithm, we can decide on a bunch of coins we want to flip and their corresponding biases. So we must decide what number of coins we want to flip, and for each of them, what the value of r is going to be. And this is a purely classical step. We fix this. And then in the second step, the quantum step, we do these Grover iterations, which here corresponds to preparing all the coins and then flipping them. And this is the step where the non-adaptivity is crucial, because an algorithm that uses non-adaptive Grover iterations would prepare and flip all the coins at once. Whereas one that uses adaptive Grover iterations could flip some of the coins, look at them, and then decide what are the bias of the remaining coins and whether to flip them or not, or so on. Whereas here, we have to prepare and flip all the coins at once. And then at the end, after we've done this quantum step in one shot, in parallel for all the coins at once, we can determine k from the coin flip results. And yeah, the goal is, if we are allowed to only use non-adaptive Grover iterations, we want to determine k from this set of coin flip results that we've got. And this is, again, a classical step. So the motivation for studying how to do this problem with non-adaptive Grover iterations is that it is in some sense simpler, because we don't need to, again, we don't need to do a bunch of Grover iterations, look at the outcome, and depending on that, switch to do a different set of Grover iterations or not. We can predetermine at the start of the algorithm exactly what we want to do and execute all of those Grover iterations in parallel as needed. So let's restate the problem slightly in terms of a Grover schedule that we will now define. So a Grover schedule comprises two sequences, a sequence R and a sequence T. R, so the ith value of each sequence corresponds to some ith set of coins. So Ti will be the number of coins in that ith set, and Ri will be the bias of all the coins in that set. So let's say that R of I is 5 and T of I is 2. That would mean that in our ith set, we have 2 coins, and each of them have bias 5. So we're going to flip 2 coins with bias, sine squared 5 of theta star. So one small thing to note is that in our definition, we allow the Ri values to be real numbers, but then, like we mentioned, we can only bias theta, we can only obtain odd integer multiples of theta star in our sine squared bias term. So just to accommodate this, we notate the nearest odd integer below r by this value that you see on the slides. And so performing a Grover schedule gives us a sequence of m random variables. Each one corresponds to a set of coin flips. So it corresponds to TI coin flips, each with this corresponding bias. And so it's a binomial random variable, and it is sufficient for us to retain the mean of each of these variables. Finally, one thing to note is that performing the Grover schedule RT will require at most half times sum of RI-TI many queries. And this is theta of sum of RI-TI many queries. So now, what is our goal? Our goal is to find the Grover schedule that allows us, after we've performed the schedule, to estimate k to a factor of 1 plus epsilon. But we want to make the query complexity, the total number of queries, which is sum of RI-TI, as small as possible. First, note that we don't really have any hope of achieving a query complexity that depends on k, because our algorithm is non-adaptive, it must work for all k. So our bound cannot depend on k, because at no stage of the algorithm can the algorithm take into account what the value of k is. So our actual goal should be to achieve the best possible k independent bound. And that works out to O of square root n over epsilon. And now we'll proceed to show an algorithm that achieves this query complexity using non-adaptive Grover iterations. Before that, first, let's state some assumptions. We assume that epsilon is at least 1 over n, because the case of 1 over n is exact counting, and so going below doesn't make any difference. We also have this assumption that k is at most 2 to the minus 20n, which seems like a very strict assumption, but first note that it is without loss of generality, actually, because we can always pad n to have a bunch more dummy variables, a bunch more dummy inputs that all map to 0. And this won't affect our original problem at all. So that is one reason why theoretically this is fine. And also note that our algorithm doesn't strictly require this. It could work with something like k less than or equal to n over 8. But it's convenient to assume this because it allows us to cite another algorithm as a black box. Finally, we'll assume that k, the number of elements we're counting, is non-zero. So before we tackle the overall problem, we first look at a simpler version of the problem, which is we are given two angles. Suppose we know that theta star is one of them. How do we distinguish? them? How do we figure out which one it is? And also note that over here, I'm switching from talking about estimating k to estimating theta star. This is because they are equivalent up to some factor on the epsilon. Namely, estimating theta star to a factor of 1 plus epsilon over 6 is sufficient to estimate k to a factor of 1 plus epsilon. So from now on, we'll talk about estimating theta star. Now, to distinguish a pair of angles, we can do the following. If the angles are theta and theta times 1 plus gamma, we want to prepare a coin with some bias such that if our actual angle theta star were corresponded to angle theta, we would rotate until that bias would make us rotate until the angle is like some 2 pi k. And if our actual angle were actually 1 plus gamma times theta, it would make us rotate till 2 pi k plus pi over 2, or roughly there. So then after preparing such a coin and measuring it, if we get an input that maps roughly to 1, we'll know that maps to 1, we'll know that likely it is a coin that is 1 plus gamma times theta, or that is likely the angle. And otherwise, we'll know that the angle is likely theta. So this is an implication of the rotation lemma from Aronson and Rawls' paper in 2020. And we can distinguish these two angles using a coin with r set to O of 1 over theta times gamma. So that's how we can distinguish one pair of angles, but we need to do a little bit more than that. We need to okay, so our overall goal is to determine theta to some factor of epsilon. Rather than straight away achieving this overall goal, we first have a temporary assumption for now. Let's assume that we are given some angle theta prime that is close to theta star, and close meaning just like a constant factor away. So it's not like a 1 plus epsilon factor away, but we know it's at least at most a constant factor away. Now we want to set an intermediate goal of distinguishing any two theta that are possible candidate values for theta star, meaning that they're between theta prime over 1.11 and theta prime times 1.11. You want to distinguish any two theta in this range that are at least a factor of 1 plus epsilon over 6.1 apart. Again, note that the reason for epsilon over 6.1 is because we want to estimate theta star to a value of 1 plus epsilon over 6. And so trying to distinguish angles that are even closer than that doesn't make sense. The point one is just to give us breathing room later on in the algorithm, as we'll see. So a first pass idea would be to apply an idea similar to the rotation lemma as is, meaning that we define a schedule. So let's define a sequence U, which is 1, 1.01, 1.01 squared, so on, geometrically increasing until 1.2 pi over theta prime epsilon. So in this sequence, so we'll set our Grover schedule to be exactly this sequence. For now, we don't worry about what the T schedule is. This is our set of biases. And what happens is that using this sequence, we can guarantee that for any pair of candidate angles, there will be some coin that we have prepared that separates these angles by pi over 8. And so this means that we can guarantee that no matter what two angles we are asked to distinguish, there's always some coin for which they are far apart in terms of their angle. But this is not sufficient. Angles might be far apart, but the coin probabilities could still be indistinguishable. Like they could be at pi over 100 pi plus pi over 16 after rotation, and 100 pi minus pi over 16. And so their probabilities would still be the same. So an improved idea that gets around this is to add some offsets. So for each I, so for each UI sequence, so for each I that we have in our UI that we have in our sequence U, we can add, instead of having one entry there, we can add a bunch of terms of the form. So these are the AI0, AI1, all the way to AIC plus 1 terms. And so we define this new sequence, Sij equals UI plus Aij for all I and j. And the idea is that first we look up the UI that we wanted previously. And we see whether it gives us two angles that are in the same quadrant. We're guaranteed that the UI will give us angles that are pi over 8 apart, but we also want them to be in the same quadrant so that we know that we won't hit any case where we can distinguish them in terms of angles but not probabilities. If that happens, great, then we're done. If not, then we use these extra offsets that are large enough so that they can, so that there's always some Aij that rotates both angles to be into the same quadrant, but small enough so that the separation is still pi over 8, approximately. And so these offsets get around that initial problem of not being in the same quadrant. Based on this, we now have a lemma for distinguishing angles, which is that given two angles, theta naught and theta 1, there's an O of 1 time algorithm that either outputs reject theta naught or reject theta 1. This O of 1 time algorithm basically just looks at the two angles and determines what value of UI or what value of Sij to use and looks at the appropriate conflict, and it rejects the less likely one. And we can show that the failure probability is at most O of 1 over log 1 over epsilon. This failure probability comes from the T sequence that for now we have ignored, and later on we'll see why we've defined it the way it's been defined. So the failure probability is 1 over log 1 over epsilon, and the failure condition is that if theta b is very close to theta star, then the algorithm will not reject that theta b. So now we have an algorithm that can help us to distinguish a pair of angles. What we now want to do is we want to consider all angles in our range of candidate angles. We split this range into geometrically into like sequences that are 1 plus 001 epsilon, 1 plus 0.001 epsilon for, distance away from each other. And so once we split this range into a bunch of angles with finite enough precision, we run a tournament between all those candidate angles. And each match in the tournament essentially involves using this lemma, this distinguishing lemma, to eliminate one of the angles. So the tournament proceeds in this tree-like structure where note that we need to first sort all the angles. And suppose there are 8 angles, then we'll pair up the first one with the 5th one, the second one with the 6th one, and so on. And then we'll run all the matchups in the at the bottom of the tree. And then after that, we'll proceed to the next layer. Now 4 of the 8 angles that have been eliminated, we have 4 left. Again, we sort, again, we do matchups and so on. And then at some point in this tournament, it might be the case that we see a void matchup. The void matchup is one where we are matching up 2 angles that are already very close to each other. And at that point, it doesn't make sense to match them up anymore, right? So then we stop this first stage of the tournament and enter the second stage of the tournament, where every angle essentially plays like a round robin, and like it plays every other angle, and we eliminate any angle that loses to any other angle. So any angle that even loses once, we eliminate. Some angles, so there'll be some set of angles remaining, and all those angles in that remaining set will not have played against each other, meaning that they will all be part of void matchups. This means that they'll all be within like some range of 1 plus 0.001 epsilon of each other. And this is great because now we can output any one of those angles, and this will be how we pick a winner from the tournament. So the probability of failure is equal to the probability that the angle that we want, whose angle closest to theta star, loses a matchup. The probability of losing a matchup is O of 1 over log 1 over epsilon. Recall that we got this based on how we defined T in the Grover schedule. We got this failure probability. We can derive it using Chernoff bound. And so since the probability of losing each matchup is at most this amount, and there are at most O of log 1 over epsilon matchups, we can show this. We can union bound to get an O of 1 failure probability, and we can make this whatever we desire, let's say like 1/3 or 1/4, by tweaking the value A that we used in the Grover schedule for the number of conflicts, which is a constant. So now let's do some accounting and figure out what the query complexity of our algorithm is. It's very close to what we want. Essentially, we have an extra log 1 over epsilon factor that we really like to get rid of. And again, the trick to get rid of it is by slightly modifying T. And with some like simple but tedious modifications, we can eliminate this extra log 1 over epsilon factor. So now we have an overall algorithm that, given some theta prime estimate, constant factor estimate of theta, it works well. It gives us a 1 plus epsilon approximation of theta star with high probability. So this is a major part of the overall algorithm. But the overall algorithm itself, what it does is, in its first step, it gets a 1.1 factor approximation of theta star, call it theta tilde. In the second step, it considers all possible theta prime values with which it can run this algorithm that assumes theta prime is close to a constant factor away from theta star. And it just runs all those runs that algorithm for all those possible values of theta prime. And this turns out to be okay in terms of query complexity because we can make the values of theta prime that we try out geometrically increasing. And also note that we can do step 1 and step 2 in parallel. So we maintain the non-adaptivity. And then finally, in our classical post-processing, what we're doing is we're picking the value of theta prime in step 2 based on what theta tilde was in step 1. So we're picking the actual we're picking something that's actually a constant factor away from theta star, and then using the result of the tournament that we looked at in that iteration and outputting the value of theta star that we get from that. And so this is how, maintaining the non-adaptivity, we can produce an estimate of theta star and hence k to a constant factor, to a factor of 1 plus epsilon with optimal query complexity. Thank you very much for your attention.